All right, and the next speaker will be Harald Werner from Efinix. Efinix is a semiconductor manufacturer specializing in programmable logic devices, and Harald will talk to us about the innovative architecture of their latest FPGA device family.
Okay, it's not this one. Control L.
F11, I keep forgetting. F5. All right, thank you, Harald.
Thanks. Can you hear me? Okay, good. So today we heard a lot of examples from the market leader on FPGAs. Now I will show you an alternative from Efinix. So we are an FPGA manufacturer, and we have not a Me Too product. We are differentiating our products with a special architecture, and we are calling it a quantum architecture. First of all, we are an American-based company. Our headquarters is in Cupertino, just around the Apple Circle, and we are founded in 2012. We have roughly 200 employees, so really small for an FPGA company, but we have a very efficient architecture which allows us today to do really very good FPGAs with such a small employee count. So we have development locations in US Cupertino, in Toronto, Canada. This is mainly for place and route stuff. And then our largest development location is in Penang, Malaysia. Our headquarters for EMEA is located in the north of Munich. Distributors, I will skip some foils which are sometimes not of interest for you. Usually, if you work with FPGAs, I think a top issue or top topic is timing closure. Why does these FPGAs have sometimes problems with timing closure? Is a lack of routing resources. And you can compare it like an autobahn on highway, where you have a lot of cars on the highway, more and more cars coming on the highway, and nobody is leaving the highway. Then you will get a traffic jam. And similar happens if you do routing in an FPGA, because you only have a limited amount of routing resources. And this takes a lot of the die size. What we did is a different approach. So if you look here at the standard approach from all the other vendors, and this approach is roughly 30 to 40 years old. You have fixed routing, you have fixed logic, and you have to provide a lot of routing to make it possible to do a connection from A to B. Usually, it's calculated for 75% of utilization. Sure, you can go up on the utilization, but then the system speed goes down because you cannot use anymore the direct connection from A to B. With our approach, on the right-hand side, the quantum, where is it? That's a long delay. So we have a different approach. We do not have all over the chips routing resources. We have cells which are able to do logic and routing at the same time. That means we can provide routing in the area where it's required. So if the design is more on the right top corner, we can provide routing there. And this makes it possible that our die size is comparable to the market leader, less than half of the die size, with the same functionality and sure in the same geometry. We are staying with a LUT4 architecture because we believe this makes our FPGAs much less power hungry than a LUT6. Our approach is as well silicon process agnostic. Means we are taking the silicon process as we are getting, for example, from TSMC, putting it to our architecture, and they can produce our FPGAs. Means it makes it really easy for us to change the fab, maybe TSMC Taiwan today, tomorrow we can go to TSMC in Japan, or even to Europe if they provide the 60 nanometer process in Europe. With our approach, having half of the die size, we can deliver as well small packages. So usually our products are done for the edge. Means the edge needs small packages and low power. And this is exactly what we can offer with our architecture. Then, as our die is smaller, the distances are shorter. Therefore, we can as well have high performance. And this is what our architecture gives us for our FPGA. So all our FPGAs are based on this quantum architecture. Here you can see each cell can handle logic and routing. Sure, if you have areas which needs more routing, then maybe you cannot use the logic anymore, and so vice versa. Then some of the cells you have to use for routing, and this you have to calculate in your calculation. Rule of thumb, 5 to 10% of the logic cells of a titanium or a topaz family you can calculate for routing. But it's design dependent. On the right-hand side, you see a floor plan where you see the blue cells, which is usually logic, and the orange cells are usually routing and logic. These are the three families. Trion, this was our first family based on 40 nanometer. Then we moved to titanium, which is 60 nanometer TSMC. And then topaz. This is something for high volume opportunities. I usually say it's a low-cost version of titanium because we spec down the speed. And if you spec down the speed, you are able to do much cheaper substrate, means the combination or the connection between package and the silicium. Therefore, today we will concentrate more on the titanium stuff because this is what I heard. This is of interest here at CERN. All the families can be done with our tool chain, Efinity. And you do not have to download 100 gigabyte. You have just to download 1 gigabyte. You need 3 gigabyte disk space. There's no license behind. Just register on our web page, and you can download the software. And you have a whole flow from RTL input to the bit stream for all our FPGAs. So this is the first one, Trion. We'll just cover it. T4 from 4,000 logic elements up to 120,000 logic elements. So the name gives you roughly the size of the FPGA. A 4 means 4,000 logic elements, 120, roughly 120,000. So this was the first one. And so T4, T8 are some special devices in the small packages. These are lowest power devices, means they do not consume more than 200 microwatt in standby current. But these are special ones. Moving to titanium, this is done at 60 nanometer TSMC. Second generation quantum fabric means the same approach, but we optimized a bit more to speed. And this is a family which is available today. So the green ones shows you which devices are available. And the other ones, yellow one, it's available soon, means in the next few months. And we are starting here with 35,000 or 60,000 logic elements, means we offer as well small FPGAs. And here you can see the big benefit of our architecture. Look at TI-60 in the wafer level chip scale BGA 64. It's a size of 3.5 by 3.4 millimeter. Try to get 60,000 logic elements somewhere else in 60 nanometer with this small die size. Oh, stop, we have to go back. So we have devices as well with high-speed SerDes. High-speed SerDes means up to 16 gigabit. With the devices with high-speed SerDes, we added as well PCI Express controller inside, where you can do root complex and endpoint, and PCI Express Gen 1 up to Gen 4. In the same devices, we offer low-power memory controller with LPDDR4X, which goes up to 3.3 gigabit, depending on package. Not each package can support up to 3.3, maybe some up to 3, but it's written in the data sheet. As well, each FPGA with high-speed SerDes has a hardened RISC-V core inside, a quad RISC-V core, which can run up to 1 gigahertz. Then we have high voltage IOs, high speed IOs, which can go up to 1.5 gigabit. And we have DSP blocks. In the big one, at the moment, the biggest device which is available are 375,000 logic elements, has up to 1,300 DSP blocks, which is a multiplier 18 by 19, accumulator behind, similar to DSP48 functions, which I'm pretty sure everybody knows. What we have special here as well are some SIP packages. SIP is system in package. What does it mean? I will go to the next one. Here, for example, TI-60F100 SIP is a package 5.5 by 5.5 millimeter, which has 60,000 logic elements, includes a HyperRAM, 256 megabit, and SPI flash. So you have a single system with 60,000 logic elements, with memory, which can be used for internal processor as well, and an SPI flash that you have a single chip device. Going back, we have a second SIP. It's called TI-180. And we did a similar approach, but not yet with HyperRAM, because HyperRAM is limited with a bandwidth. TI-180 has a low-power DDR4 memory controller. Therefore, we put a low-power DDR4X memory into the same package. So now you have a 15 by 15 millimeter package with 180,000 logic elements and 2 gigabit of memory, which can run up to 3 gigabit. Our largest device has up to 16 gigabit SerDes channels, 2 PCI Express memory controller, which can go up to Gen 4, and this hardened RISC-V. And sure, available in different packages. We have as well projects at CERN which already using our TI or titanium FPGA. For example, in this project, they are using our TI-60 on a die level, and they are checking the radiation tolerance of these devices as well the SEU sensitivity. Okay? Not sure if somebody is knowing this. So here's a SIP device of TI-180. And the big benefit of a SIP device, for example, here on the TI-180 is you gain additional user IOs if you are implementing the memory into the package. And you save a lot of time to do the layout for a low-power DDR4 memory. And as well some money, because maybe you need less layers for your PCB. And you only can do this approach if you have an FPGA which does not consume a lot of power. Here are some packages we can go over. Here a quick overview of the TI-375. As I told you, 16 gigabit high-speed SerDes. We support PCI Express controller Gen 4. We have MIPI. If somebody is using MIPI, we are supporting up to 2.5 gigabit 4 times. And important as well, the low-power DDR4 memory controller, which can go up to 3.3 gigabit as well. This is not a bad number. And LPDDR4X has as well a very low power consumption footprint. We have these devices as well available for automotive applications. I know you are not doing automotive applications, but it means as well for this family, it can go up to 125-degree junction temperature. Maybe this could be beneficial for you. And again, all FPGAs with SerDes will have a quad RISC-V implemented as a hardened function. And we are doing a different approach like the market leader. So they have a big computer system and added an FPGA. We have an FPGA, and a small area is our RISC-V. Means we only implemented the RISC-V with 4 cores. Each core has an MMU, so you can run easily Linux out of it. And every peripheral component will be added via AXI to the RISC processor. And the big benefit what we have is, again, we are focusing on low power. So having this device running with 4 cores at 1 gigahertz, we do typically not need more than 500 milliwatt. Compare this, what is available at the others in the market. Topaz, as I told you, these are the lower cost families with lower speeds for high volume applications. Therefore, I'm pretty sure not of interest here. What does our architecture gives you? Sure, small packages because of the small die size, but as well low power. Here are some power numbers for our Trion family. And here are some power numbers for our Titanium, maybe of interest here, TI-375, with PCI Express Gen 4, with 1,000 multipliers, and the system is running at 200 megahertz, with low power DDR4, running at 3 gigabit per second. We have a standby current with roughly 100 milliwatt. And in action, it goes to 4.8 watt. And if we are using the low power version of the FPGA, we are even in the 4 watt area. And if you compare this to the other ones, then you will see where is the benefit of using our devices. RISC-V, we are supporting the hardnet RISC-V, but as well soft IP RISC-V and the Sapphire SoC. The RISC-V is running at 350 megahertz in our FPGA fabric. Okay, just I go through all the stuff. So if somebody is interested in AI functions, we have as well ease of use AI functionality, which is based on RISC-V. Means you can run it on a RISC-V, but you can as well accelerate each layer of your TinyML network. And this, we are using custom instruction from RISC-V and a DMA approach, which gives us more a parallelism to the FPGA function. We have development kits for all our FPGAs. Here's our largest one with PCI Express, with an SFP Plus cage where you can easily handle 4 times 10 gigabit Ethernet, but as well 40 gigabit Ethernet. Software, what I told you, free of charge. Just register on our webpage and you can download it. It runs under Windows, it runs under Linux, and it's a whole flow. What is not included is a simulator. So, but we are supporting all standard simulators like Aldec, like Mentor, ModelSim, Questa, like Synopsys VCS, and as well the Cadence simulator. Okay, I think this was, so we have as well a debugger, what you know as signal tab, signal scope. So it's implemented as well in our software. Just select the signals you would like to trigger or trace, put in a trigger condition. If the trigger condition happens, we are generating a VCD file and using GTK Wave, an open VCD viewer, which shows you the waveforms. Okay. I think this was, so I added a lot of slides that you have something to read. Maybe here, important stuff as well are the requirements for our software. So download, 1 gigabyte. Disk space, 3 gigabyte. Memory, even if you would like to do the 375, which means 375,000 logic elements, 16 gigabyte on memory, not more. Okay, thanks. Questions?
Thank you very much, Harald. So any questions, please?
Weird setup, sorry. Could you comment, please, on the links, the solution that you have for high number links?
Again. Say again. It's
the high number link solution that you have.
So we have 16 gigabit SerDes channels.
16?
16.
Okay.
2 times 16. 16 SerDes channels at 16 gigabit.
Okay, thank you very much. And about the RISC-V, is it full system-on-chip control of the similar to Zinc?
Yeah.
So practically the same functionality for everything on the board, even configured FPGA?
I would say yes, but we can discuss it at the table in more detail.
Okay, because it's one main feature. Thank you.
Yes, please.
Do you plan to provide a 100 gigabit Ethernet interface?
Yeah, so we are working on, so I showed you here the table, and we are at the moment at 375. And sure, we are working as well on the right-hand side stuff. So at the moment, we are in the specification phase of the TI-1000, which has more SerDes channels and sure will go up to the faster speed. But this is at the moment the specification phase. But it does not take 3 years time to do this. This usually takes 1 or 1.5 years for us to finalize also first samples. And especially if you look at the TI-375, it worked at the first time. We got samples back, we were surprised as well, but everything worked. And this would be then the 100 gigabit 4 times 25 gigabit. So not one channel at 100 gigabit. Additional questions?
Anybody else? Davide?
So I think, so thanks a lot for the presentation. So one thing that every developer that worked with Xilinx faces is the long time for compilation. So I was curious for one of the largest FPGA that you provide, let's say with 80%, 70% resource usage, how long would it take?
We got feedback from our customers that our runtime is half of the market leader runtime.
Similar size?
Yeah, sure. Yeah.
There was a question over here. Yes, please.
Yes. Do you provide something like chip scope or an integrated logic analyzer?
Yeah. This is our debugger. So the debugger, you can select the signals from your design on RTL level. Say, okay, these are the signals I would like to trace. And then it will be automatically integrated. And then you can put on some trigger events. And if the trigger event happened, we are writing out the VCD file where you can see all these internal signals. Okay?
Buck, yes, please. Not much, no.
Okay, I think now you can hear me. So I was wondering, what's the situation with Linux support? Is it, do you have some example designs? Do you have driver support for all of your hard peripherals in these devices?
You're referring to Linux support for RISC-V, correct? Not for the
Yes.
IDE system.
Yes.
Okay. So we are supporting the build root Linux, and this you can download from our web. We have examples for this. Sure, we do not have now all these 20,000 drivers available. Think about it, we are a young company, but we are growing in the right direction. And check with us if you need a special driver, what will be available in the future, and we can quickly change our priority list.
Okay, thanks.
You're welcome.
Yes, please.
Yeah, thank you so much for the presentation. In the place where I work, usually when we need to buy a board or something like that, one of the things that we thought is about the flight, the flight proof or the radiation verification. Practically, how is the behavior of the board under radiation or during a flight? Do you have something like that in the company? Maybe I'm not explaining me very well.
What do you mean with evaluation? Do you mean evaluation boards or how we do our characterization?
No. See if the behavior of the board under radiation is the same or not.
Okay, radiation. Got it.
Sorry,
So,
maybe.
sorry, my fault. Sorry. So at the moment we do not have radiation tests with our FPGAs. So I told you we have a project running at CERN where they would like to test our behavior with a TI-60 die in the radiation environment and checking the SEU sensitivity on this. They told me they will finish it until end of the year. Then we can send the information here to the guys. Then they can share it.
Perfect. Thank you.
All right, let's have a last question, and then the rest we can keep them for the dinner or the coffee break.
All right, yeah,
please.
this is a quite simple question actually. So I keep hearing the word quantum in your presentation. What do we mean by quantum in this case?
It has nothing to do with quantum, what you see or mean in the physics. It's just a name. It's our quantum architecture. We just need a name for our architecture, and quantum sounds at this time very nice to us. So nothing behind.
I appreciate honesty. Thank you.
All right, let's thank the speaker again.